Hello everyone and welcome back to my channel. In the last video, we talked about how the training of a large language model is done. In the first step, there is something called a self-supervised learning where where the model learns to predict the next word of the sentence, which we did in length in the last video. If you haven't checked that out yet, I highly recommend you to go and check it out first, where I go in depth about the structure of the transformer model and how it is worked for next word prediction. So in the end of this last video, we're able to generate the next step by giving some input text. For example, here a key player in mitigating the greenhouse effect. I trained it on a corpus of text, and this is the text I started with, and with that the model could fill up the rest of the sentence as long as I want. But this is not very helpful. Why? Because we want to create a helpful chatbot, and this just filling out the next sentence or filling out the sentence that you started is not very helpful for us. For example, let's look at a Medium post. So what happens, like after first stage of LLM training, where we train it on just a corpus of text. So for example, if you give it what is capital of France, it will give what is capital of Netherlands. It's not very helpful, it given the sample data. But what we want is, if we ask it what is the capital of France, it should answer Paris. That's what we want to do. And that is achieved by something called as supervised fine tuning or instruction tuning. So during the training of this model is going to be exactly same as the previous case what we did. It is just going to be predicting the next word. For example, if we give it input user, it should predict hi, something like that. So what we hope is when we infer from this model, we'll give this much as input, and the rest we expect the model to complete in a very semantic way, just because we have trained it on similar kind of data. Alright, so let's go to Jupyter Notebook and see how it is implemented on the small language model architecture that we do. We imported some libraries, then I imported the tokenizer. This is from GPT-2, because you know tokenizer in the end is nothing but just a dictionary who looks up for each word a corresponding token. And this is my dataset that I created. In my dataset, I have 3 questions and 3 corresponding answers. So for example, my question is what is AI, and the answer is AI stands for artificial intelligence. Then how does deep learning work? It uses the neural network. Then what is an NLP? And NLP stands for natural language processing. This is the 3 question and answer pair I have, and I use this to train my let's say a simple chatbot or a language model on instruction fine tuning. So how do I do? First, I'll create my input data. I'll format in a way. So I'll format like this. So I will first add an extra prefix that this is the question. Then I'll put the first element of this question list. Then slash n, this will like add a space, answer, and then the answer, and then my end of sentence token. So what does my sample looks like? My sample looks like this. Question, what is AI? Answer, AI stands for artificial intelligence. Then end of sentence token. Alright. So now I will feed this to my model. And how do I feed this? I'll just shift it little towards the left. We'll see exactly how it is done in the following steps. And before that, let's fix the context length of this language model. Often I think you have heard that this language model has 1 million context length. That means you can at one time pass a text of 1 million tokens into the model and you get the output. But for this case, I'm just setting it to be 50 tokens at max. Let me run it. And then if I use my tokenizer on this sample text that I have, and I get the input IDs, this is basically the tokens. See, this is the corresponding input IDs for the text I have here. Alright. and the shape is 17. All right. But because I want to train my model in batches, so that's why I want all the input data in one batch to have a similar length, because when I use train loader to get a batch of data, it gets a batch of tensors, and in one tensor there cannot be a sample having 15 tokens, another having 50 tokens. They all have to be the same dimension. That's why we need to pad them to a certain length, and in this case, which is my context length, and this is 50. So that's what I did here. I padded my token. I padded this particular sentence to have 50 token length. So now let's have a look at it. See, now it is padded with the end of sentence token. But there is one catch here, is for the rest of the tokens which are padded, I do not need to calculate the loss because they don't mean anything. As long as my model predicts up to this part correctly, I'm good. I don't care if the model predicts pad token for the rest of it, because it doesn't make any sense in the accuracy in the end. So that's why I would like to ignore the rest of it. And for that, I get a very neat trick which is already present in this tokenizer class. So what happens when you get this particular output? You get two outputs. One is the input IDs, the corresponding tokens, and along with that you also get something called as the attention mask. So attention mask refers to where the attention mask is 1, that refers to there is actually some token in there, and where it is 0, this basically represent the padded tokens. So we can ignore that during our loss calculation. And to ignore that, we just replace those tokens with -100. And I'll tell you that why particularly -100. Alright, so this is what I did here. So here you must have seen that instead of sequence length, I did sequence length plus 1. It's very important to understand why I did that, and I'll explain that in the following cells. Alright, so the output of this tokenizer, I saved it in something called tokenizer output, and it has two methods. One is the input ID and the attention mask. I acquired both of them. And for example, what will be my input to the model? My input to the model will be this tokenized text starting from the first token until the last token. I'm not counting the last token. You see, so now this becomes my sequence length because I'm excluding the last token as my input. And my target token will be from from the second sentence onwards to the last one. So you see here, this is my input token and this is my output token. My output token is just a little left shifted of the input token, because that's what I want. When the input is this, I want to predict this. When my input is this 2, I want to predict this. When my input is this 3, I want to predict this, so on and so forth. So that's why I put sequence length plus 1, because I'm going to sacrifice one token anyway. That is it, by the way. We have understood everything that we need to know about supervised fine tuning. Now the rest of the process are going to be exactly the same that we did in the previous video. For example, I created a transformer model. For the sake of completeness, I'll just go through them roughly. If you want the detailed explanation of this simple model, you can check out my previous video. There I have gone by each and every layer and how they what is their significance and how they change the input. All right, so let's see what we have. We have a very simple transformer language model. I inherit it from the Torch's neural network module. To start with, I have an embedding layer which maps all the vocabulary sizes to a particular embedding size. This embedding size which I define. Then I define a positional encoding, because the transformer architecture does not have any sense of which token came first or second if we do not add this positional encoding. So that's why it's important. And in this case, I kept them learnable, that I did not fix any particular positional encoding such as sinusoidal or something else. I just let the model learn it. Then this is my encoder layer, which is a very neat uh, implementation present in the PyTorch. Here you specify the embedding size, the number of heads you want in your transformer architecture, the dimension of the a fully connected layer inside the transformer, and batch first. This batch first is important just for the because it expects the input to have batch as the first dimension. And after that I initialize a fully connected layer. So this is my language head, for example. So this one will have embedding size and map to the vocabulary size. And here, whatever is the maximum value given by the model, I'll take that to be my next word prediction. And then a simple forward loop. All right. And these are the hyperparameters I have chosen for this particular model. Embedding size of 64. I choose 4 number of heads. The hidden dimension 128. I want to run it for 1000 epoch. I choose the batch size to be 4 and the learning rate is 0.01. Now I'll just go ahead and run it. And let's see whether our model works or not. So for that, we'll just pass it the input tensor that we created here. This is the input tensor. We pass this is the output. So my output shape is 1 cross 50 cross 50,257. But what I care only about is the last word. So what I did is I took the argmax for each of the tokens present, and this is what I got. But I just care about this last token to be specific. All right, and now let's see what is the point of so here, because I want to replace these padded tokens with -100. And why am I doing that? Because if you go to the torch cross entropy loss function, here you will see here the ignore text is -1, ignore index is -100. If any label has -100 in there, it does not include it in the loss calculation. So that's why. So before, right now, till now, I have not replaced them with the padded token, and right now my loss comes out to be 588. All right, so now let's replace the padded tokens with -100. So now I have replaced the padded token with -100, and now let's calculate the loss again. This is my output. See, it immediately dropped. So that's the difference. It just it ignores all the tokens with -100. All right, and now we come to the final. We put together the data loader, the data set, everything together. And yeah, this is my custom data set. It's pretty simple. What I did before, I just created a sample from my question and answer list. Then I used my tokenizer. I created my tokenized text and the mask. Then I shifted my tokenized text towards left to create my target. And then I replace the padded token with -100 so that I won't calculate them during the loss. And that's my input sequence and the target. And then this is the model, the transformer model. All right. So now comes the training part. The training part is pretty straightforward. I just copied and pasted many of the things that we have seen till now. This is the extra part that I initialized my custom data set. It takes the list of questions and answers, the sequence length I want to have. In this case, I put it to be 30, and the tokenizer because I want to tokenize it. Then I initialized my model and passed it to the GPU. If you do not have GPU, then you can just delete this like this. I initialized my loss function and the Adam optimizer. After that, this is my training phase. What I do is I pass my questions and answer. This is basically the input text and the target text. I create a mask. This is the causal mask because I do not causal mask in the language model because I do not want the future tokens to influence what the previous tokens know for their prediction. I also explained this in detail in my previous video. I recommend you check that out. Then I pass it through my model to get the output. I calculate the loss function. Then I calculate the gradients. Then I use those gradients to optimize the weights, and that's it. That's then you run the loop, and we see that the loss keeps on decreasing. That means our model is learning something. After, let's say, 1,000 steps, 1,000 epochs, I go to 0.16. Now now comes the main part, that evaluation phase. How will you evaluate? So for that, we'll have a look towards it. For example, yeah. So now let me print sample. So the sample is question, what is AI, and then the answer. So what is this sample? It's just this question and answer pair. What is AI and answer? This is going to be the input to my model, and I want it to give me the answer, which is basically a sentence completion task by now. So I tokenize them, converted them to a pytorch tensor, and I just pass the input IDs. So here I have the input sequence, and I clone it to keep it in the generated text sequence, because whatever will be the next word predicted, I'll append it to this generated text, and it will go on for, let's say, 20 steps. Alright. So in here, what I'm doing is I'm passing this generated for the first epoch. This generated text is just going to be this one, the input sequence, or this part. And why I'm taking -30? Because this is my context length. I'm taking only up to the last 38 samples into account, because that is the maximum context length I have. Then whatever the output I get from this output, so for example here, let's see what is the output. So output, as you see, is the probability distribution over 9 tokens, but I don't care about all of them. I just care about so this is the predicted token for the first input. That means question, what is AI, answer. Then the after answer, this is the predicted token. See, the output from this is AI, and that then we'll add AI here, and then whatever is the modified generated text, will then pass it to the model again, and it will go on for 20 loops. I'll just break this one. So like, now that we run it, we get the exact answer. It reached the end of sentence. It found the end of sentence token, so it stopped. And we go from question, what is AI? The answer is AI stands for artificial intelligence. And exactly, that was it. So what we can do right now is, let's say I change it to, let's say, the third sentence. So then you get, what is NLP? NLP stands for natural language processing. The model did not know this before. We kind of overfit it on the data, but this is for you to know that how this is exactly trained. The basic idea still remains the same, even though this is a very small model. Of course, there are other difficulties that you need to take care of when you're training a large model, and that's what I'm going to show in the future videos, upcoming videos. My goal is to show how you can fine-tune the Llama model, to be specific, because it is a pretty small model, pretty standard model. Llama 3.2, 1 billion parameter instruct model. So that is going to be our next video. If you are interested in that, please give it a thumbs up. It will motivate me to bring that video faster.